My guest today on Podcast for Inquiry is Professor Katherine Richardson. Katherine is a professor of biological oceanography at the University of Copenhagen and a pioneer in developing Earth system science. Her research focuses on understanding how interactions between biodiversity and climate control the overall environmental conditions on Earth. She is a core developer of the Planetary Boundaries framework. Currently, she is chairing a high-level expert group advising the EU on the economic and societal impact of research and innovation. All life on Earth ultimately depends on energy and how it flows between biological and geochemical systems on the planet. Katherine and her team identified 9 boundaries which need to be respected if our planet is to remain conducive to human thriving. Climate change is just one of them. We are exceeding 6 of these boundaries, and in recent years, they are all getting worse. Katherine describes how she and her team identified the 9 planetary boundaries and why it is essential to consider how they interact instead of viewing them as independent issues. The effects of exceeding planetary boundaries are not a problem for future generations. They are affecting life today, disrupting air travel, causing severe flooding, and contributing to more frequent and powerful storms. We have the knowledge and technology to live within planetary boundaries. The question remains whether we have the will and the time to implement them. It is my honor to bring you this very important conversation with Professor Katherine Richardson. Welcome to the Podcast for Inquiry, brought to you by the Centre for Inquiry Canada, a national educational charity supporting your community for reason, compassion, and secular humanist values. You have answers, we have questions. I'm your host, Leslie Rosenblood, board member and secular chair for CFIC. Welcome. Professor Katherine Richardson, thank you for taking the time and speaking with me today on Podcast for Inquiry.
It's a great pleasure to be here.
I want to talk to you about a paper, a scientific paper that you wrote with several co-authors, but you're the lead author, and because I think it's important, and I think more people need to know what you've learned and what you're trying to share with the world, and I really want to share your findings with as many people as possible. So I think the title of your paper, we'll start with that, is Earth Beyond 6 of 9 Planetary Boundaries. And there's a lot, even just before we get even into the content, I've got a few questions about the title. So let's start with the idea of a planetary boundary. What is a planetary boundary? Can you please explain that to me and our listeners?
Yes, of course, Leslie. A planetary boundary is a guardrail that we wouldn't want to exceed if we want to minimize the risk that we humans change the living conditions here on the planet, potentially in a way that humans could no longer really, or human societies can't really thrive. And you can think about it locally, in the local environment, we have boundaries. We set a limit for how much pollution you can have, and how much, so we have boundaries locally because we've recognized that we need to manage our relationship with the local environment. When we got to be more people, then it became necessary to have regional boundaries as well, because if you want clean air and water in Canada, you can't let the United States pump all their waste into the air and water. And
Right.
you have a boundary for how much we should be allowed to perturb the local and the regional environment for
Right.
our
I
own
remember
sake.
when I was a child, there was a problem that was called acid rain that was
Sure.
killing our lakes. And then, we Canada and the United States formed a treaty and limited, I think it was sulfur emissions primarily. And it took 10 years or so, but the lake ecosystems in Canada and some in the States were restored once those sulfur emissions were reduced dramatically. So, okay.
Exactly.
So
You were
that
a
makes
child,
sense.
I was a young adult, but I remember it as well. So, Yes. So we recognize that we need to have boundaries for how much we can actually impact the local and the regional environment. And what the climate crisis and the biodiversity crisis are showing us is that we also have to manage our relationship with the global environment, just not just the local and the regional, but now the global. And when politicians go in and say we want to constrain human caused climate change to within 2 degrees, then 2 degrees becomes your de facto boundary. The problem is we don't only impact climate, we impact biodiversity, we impact water, we put out pollution. So the planetary boundaries are an attempt on the basis of science and scientific evidence of how the Earth works and how humans are impacting it to first identify the processes in the global environment that we're impacting to a degree that if we keep on pushing it, it could potentially change the living conditions on Earth. And we identify 9 different things where of course climate is one of them and biodiversity is also one of them, but it's also air pollution, it's also the ozone layer, it's how we use water, it's the release of reactive nitrogen and phosphorus and so on. So we identify 9 different processes, and then on the basis of our understanding of how the earth system, our ecosystem, how that system actually works, we try and go in based on how we know the earth has behaved under different climate conditions and so on. We try and go in and say, what's the safe operating space? How much can we let ourselves impact these processes without running the risk that we undermine our possibilities for societies to thrive? So that's what planetary boundaries are. And you started with the title of that paper. I have to admit, I'm a little bit unhappy we chose that title because being on the wrong side of the boundary is in itself not necessarily a problem. In the 1990s, we were either on the wrong side or very close to being on the wrong side of the boundary for the human caused ozone hole or
Mhm.
depletion of the ozone layer. And now, thanks to the Montreal and other international treaties, we've brought ourselves back into the safe operating space.
Right.
So,
We banned CFCs,
exactly,
chlorofluorocarbons, and that
exactly.
was a global treaty, and it actually worked. Like there
It
was a
actually
substitute.
worked.
There was
Yes.
something substitute. There would be substituted something else that did pretty much the same thing. We stopped using it, and again, it wasn't immediate. Like the once we stopped, as I recall, um, it wasn't immediate. But if we looked 5 years later, the ozone layer stopped, the hole in the ozone layer stopped growing, which was good. And you go 10 or then it was maybe 15 years later, the hole started shrinking. And now I haven't heard anything about a hole in the ozone layer in
Well,
15, maybe 20 years.
it's still there, but it's going in the right direction. It's
Okay.
just
So,
things
so
take time. Things
it's
take
heal.
time.
I mean, to anthropomorphize a little bit, it's healing, right?
It, it's
It's
exactly what it's doing. Exactly
right.
what it's doing. But so being on the wrong side of a boundary isn't a problem. But you see, we started doing this or trying to develop this framework in 2009. So we had a paper in 2009, we had another one in 2015, and the one I led last year is came 8 years, obviously, came in 23, so it came 8 years after the one in 2015. And all of the boundaries that we found were transgressed in 2015 are even more transgressed today than they were in 2015. So you and I can debate until the cows come home as to whether we have actually placed these boundaries the right place. They may be a little bit more or a little bit less. But the point is, you can look at any one of these processes that we identify, pollution or climate or biodiversity loss or use of water, changing water cycles, and so on. You can look at any one of them and say, oh, yeah, I can imagine a world where we couldn't be here anymore because of climate. Or, oh, yes, I could imagine a world that would be so polluted we couldn't be here. So we know there has to be a limit and or a boundary for a safe operating space. We don't know exactly where it is, but we
Hmm.
know that there has to be one. And the fact that we are barreling out of the axes here. So we're pushing harder and harder and harder on these processes is just plain bad news.
All
Whether
right.
so
I want to get I want to get
super
into
interesting.
these details, and I promise we're going to come back to that. But I've got a few more foundational questions. I want to
Sure,
set
sure,
the
sure.
stage a little bit. So I'm not a scientist. I took a couple science courses as an undergrad of physics and biology, but I'm not a scientist. I like to think of myself as scientifically literate, and I think that is a fair description of the majority of our audience. Every time I think of ecology, so the environment, plants, animals, how they interact, uh, it's complicated. It's very complex. That everything is happening on multiple levels simultaneously, and everything affects everything else. It's very complex. The fact that we understand anything about uh, about nature is in some ways astonishing to me, and that's thanks to, in part to, well, almost entirely to you and people like you. So when we talk about there has to be a limit to how humans change their environment before the environment changes in a way that either we can't control or is going to come back to bite us because we're going to change it in a way that's going to be harmful, make it worse for our either ourselves or our collective descendants. How did you come up with planetary so there are limits out there? Sure, like that. I think, but how do you find them, and how do you say there's nine of them? Why not six or 20? And then what? Like, did you come up with what the boundaries were, and it happened to be nine? Did you choose nine and figure them out? And can you tell me a little bit about what that process was to
Sure.
determine what what are planetary boundaries, right? Because like if you're I mean I can just off the top of my head I can think of like 20 things. I can probably, and if I put some work into it, I can probably think of 50 things that we depend on as human beings, on the planet, on our environment, on our surroundings, on each other. So in some ways I'm amazed that there's only nine and not hundreds. So how did you determine them? And I'd like to know how you brought it down to just nine planetary boundaries. That's a tractable number, and I'm surprised that that if we did these nine things, we'd be probably okay. Help me understand how you took this enormous planet with staggering complexity and reduced it down to a comprehensible nine things.
Well, we started actually. Well, first of all, it's important to say that the planetary boundaries are not intended to replace local or regional management. So it's local and regional environmental management, which would take a lot more of the detail into the picture, the complicated detail into the picture. But for the planetary boundaries, we started by Johan Rockström got a group of people together in the Tallberg Foundation in Sweden in 2008, I think we met, and we said, what's important about making this ecosystem of ours, which is the Earth. I mean, an ecosystem is defined by organisms in contact with each other in a physical environment. The global market means we're in contact with every other person on this planet and every other living being. So the Earth is our ecosystem. What are the really important things for that ecosystem to make it be as it is? Well, it's the energy coming in. It's the energy balance. And you then, well, what are we pushing? What are we hurting in terms of the energy balance that, could make a difference? Well, then you get to climate and air pollution and particles in the atmosphere and the ozone layer, that's also an energy thing. And then you say, well, what's different about this planet and every other planet? And that's, of course, the fact that there's life. And it's the interaction between life and the energy that actually creates the conditions on Earth. And so then you need something with life, and that becomes biodiversity. But just numbers of species isn't enough. What do we do that impacts life on this planet? Well, we fell forests. We use land area, and that's also important because first of all, yes, it's important because it impacts climate because it can store carbon or not store carbon if you fell the forests. But we don't know what life is but we do know what life does. And what it does is it moves around all the non-living elements on Earth that are left over from the Big Bang. Those same elements are found on other planets as well, but there they don't react very readily with each other. It happens if there's a lightning strike or something, but normally they just kind of sit and look at each other. And on Earth, that doesn't happen. I mean, some people say that Neil Armstrong's footprint can still be seen on the moon for very good reasons. I don't know if that's true. I've never been there. But I do know if you had a footprint on the Earth from 1969, it would be long gone. Not least of which because we have life, and life moves around, it mobilizes. Um, uh, well, that's what organic chemistry is and biochemistry is. When we study it, we understand the processes going on there. And every time it's been possible to get enough free energy out of a transformation of these elements to support life, then an organism or an organism group has gone in to do that job. So we kind of built it up from the bottom and say, okay, energy, okay, life, and what is it that, pollution, that's not a good thing for life. That's one we gotta look at too. So it was, we built it up that way. And you're absolutely correct that we probably could have chosen other measuring points. But we do believe that with these nine, we have captured at least proxies for all of the processes that are really interesting, because really the processes are energy and life. And you could have had an yeah, you could have an ice boundary, and or you could have had a but we capture the ice, actually, we think, in the climate boundary and the radiative forcing. So it could have been put together differently, but the object of the exercise is to identify the relevant processes that are keeping the earth in the state, in the environmental state it is in the moment. And it's very important to mention, because people say this all, oh, but the world has been warmer before, or it's been colder before, and blah blah blah. The thing is, that's absolutely true. The earth has
Mhm.
been snowball earth or hothouse. I mean, it's absolutely true. But people haven't been there. Humans haven't been there under those
Right.
conditions.
So it's great that the Earth was much hotter before or much colder before, but we're like a Goldilocks species in the sense that like one of the key things about life is homeostasis. If we are too hot, we die. If we're too cold, we die. And given the range of temperatures that exist, we are comfortable as people in a very narrow range of temperatures. And if we go beyond, if we get too hot or we get too cold, sure, the Earth might be fine, but
Oh, the earth's
humans
gonna be
won't.
fine.
But humans won't be, and if we care about human thriving, we need to keep our planet within that fairly narrow range of acceptable temperatures for our physical bodies. Is
But
that is that
that
right?
that is actually the only normative part of the planetary boundaries. And that is that we say, okay, humans have been on this planet in our current biological form, as far as anybody can tell, for something on the order of 250,000 years. And we survived other kinds of conditions. We survived ice ages, but it was only barely. So we went down to maybe only tens of thousands of reproducing individuals, you can see from genetic analyses. And there were maybe 10 other humanoid species, and they all went extinct in this period where the Earth condition was changing radically.
Right. So it wouldn't have taken much for humans to have gone extinct in the
Exactly.
previous ice age.
But everything that we associate with modern civilization, and we're talking Stone Age, Bronze Age, Iron Age, Neolithic Revolution, written language, the whole beeswax, everything has happened during the last 12,000 years, a period that we call the Holocene. And if you look at the Holocene period, the average Earth temperature on Earth changed by plus minus a half a degree centigrade. Plus minus a half a degree centigrade. And right now, we're already up at something like 1.5 degrees above what it was at the time of the Industrial Revolution, and we're talking about trying to limit it to within 2 degrees But in fact, at the moment, we're aiming for something more like 3 degrees with what we're actually doing. And we think this is going to be fine. And yet, everything that we associate with modern civilization evolved at a time where it was plus minus a half a degree. And many anthropologists think that this stability was really very important in humans being able to develop the civilizations that they had. And so we, as our starting, and this is normative, but our starting point for the planetary boundaries work is we say, okay, we know for certain that humanity can thrive under the conditions that the Earth has been in during the last approximately 10 to 12,000 years. We don't know for certain that humanity can thrive under other conditions, and therefore it would be exceedingly unwise to knowingly do something that could change the conditions on Earth,
So,
the living conditions on Earth.
you're speaking like a good scientist, but I think it's, because, you know, what you just said was, we don't know whether we can thrive in a, 1.5 to 3 degree increase on historical, like last 12,000 year conditions. And like,
Or
that's
even
true, but
more. I mean,
I think that's a fairly weak statement. I think it would be safe to say, and I'm going to defer to your judgment, but I think it would be safe to say is like, it is unlikely. It is highly unlikely. It is almost impossible to imagine that human civilization can survive a 3 degree increase in temperatures, because we are so dependent not just on our own individual interactions with the environment. Like, people will cook at a 3 degree average. Like, they will just die of heat exhaustion and dehydration. But also, we eat, and our food, our the animals, our plants that we eat, many of them will not survive a 3 degree increase. And if we can't grow rice, wheat, beans, then the animals that eat them, that we also eat, will not survive. There won't, the very productive fields that we have here in Canada, in the States, in Europe, in Ukraine, then, um, if all of that land becomes far less productive, if we can only produce, 3 quarters or half of what they do today, that's bad for us. So, is it safe to say that, if that our current civilization is highly unlikely, or is almost certainly going to be doomed, if we don't curb? And we're just talking about one planetary boundary right now, but if we don't curb the increase in temperatures, our species survival, or at least our species civilization, is in grave risk of collapsing, and that is the most likely scenario.
you know,
I'm just wondering if we can use stronger language than "we
okay,
don't know" if we can survive that, if
okay,
our
I'd be happy
civilization can
to.
survive that.
I don't really know why you need to talk to me because you just held my usual talk, except I usually say if we get a 4 to 6 degree increase, because I feel a little more certain there, I would say it is impossible to imagine that modern civilization as we know it can continue. And it's for the reasons you mentioned, but it's for more as well. Many of the plants and animals that we're dependent on will disappear. The storms will have enormous power, destructive power. We're already talking about putting in a new category of hurricanes because we can see that storms are becoming more powerful. But storms will be, you will not be flying. I promise you, you will not be flying because of the turbulence. Already we're seeing last year, at least one person was killed with turbulence, unexpected turbulence, and very many injured flying. And you'll have to wait a long time, thousands of years probably, because it takes a long time before all the ice melts. But if we warm this temperature by an average of 4 to 6 degrees centigrade, then you will ultimately be looking at a sea level rise of between 40 and 60 meters.
Oh my
40 and
goodness!
60 meters.
How much land would be left? Like, would that be like over half of the land that we have today? I'm guessing, right? 40 to 60 meters strikes me as that, there'd be a lot less land available and a lot more would be submerged. I mean, already we're at 70% of the planet or so that's underwater. It would be a lot more than that, wouldn't it?
It would be. I don't know the numbers. I come from Denmark where where there wouldn't be a Denmark, I promise.
Right.
So yeah. So I no, we do not believe that. No, it is impossible to imagine that civilization as we know it could continue at temperature increase, an average temperature increase of 4 to 6 degrees. So I'll go that far for you.
Okay, so this is a existential threat to every person, or or at least every person's descendants, right? This might not happen in the next 5 to 10 years, but
Oh, but
in the
it's
next,
happening now. It's happening now. The numbers of people that die in heat waves every year, heat waves that are
Mhm.
caused by climate change, or exacerbated by climate change, the numbers of people. I mean, it's like what could be in a handful of jumbo jets. And I promise you, if you lost a handful of jumbo jets, it would be the top headline everywhere in the world. But we're not
Right,
talking about all the people that already are dying in heat waves. And then we're not talking about the terrible flooding we just had in Spain, or the hurricanes that we had in Florida and Southeast United States. And I could continue. This
right.
is here now.
So yeah, so there's a couple of things here that I already know what the rejoinder to that is. One is, whenever someone dies in an airplane crash, it's always headline news. But there's dozens or hundreds that might die in airplane crashes every year globally, and there's tens of thousands that die in automobile accidents every year in the United States alone. And far, I don't know what the global statistics are, but far more. I mean, the United States is not the only country that has automobile accident fatalities, but there's tens of thousands just in the one country, probably hundreds of thousands, possibly measured in the millions globally every year. But these are like some here, some there, some there. So uh, that's always been true, and I guess heat deaths are more like automobile accidents than they are like planes crashing. The other rejoinder that I know will come is that there have always been people that are killed in bad weather events. There have always been hurricanes and tornadoes. The fact of them is not new, and they've always been they've always killed people, and we are in more places. So of course it's going, and there's more of us. So of course they're going to be affecting more people, and we have a global media system now, so that anytime anybody is drowned in a flood, or is blown away in a tornado, or dies in a landslide from a monsoon, we can hear about it wherever you are in the world. You can hear about anything that's happening anywhere. So of course we're hearing about it more. So why and that explains why we're hearing about these things more than we were, why it's impacting more people. We don't even need this alarmism about global warming and climate change. There are other factors that explain the phenomenon that you're describing.
You're absolutely, I totally respect those rejoinders. They're absolutely correct. But that what they don't address is the fact that science has also gotten to the point that it can measure storms. It can measure the energy that is in these storms, and we can clearly see that there are changes in the amount of climate change. Is only about the amount of a change in the amount of the sun's energy that you store near the surface of the earth. And over 90% of the extra energy that's now stored here is in the ocean. And very many of these storms, and not least of which the turbulence that happens when you're flying over large ocean bodies, originates from the ocean. Now, that energy, we need to track that energy. That's what it's all about. And you have to take that energy change together with all the other explanations, and say, can how much can this explanation help, and how much can that? And you simply cannot get away from the fact that we're making these tremendous changes. Listen, in the When the Earth went from ice ages to non-ice ages, about 80 parts per million of CO2 were moved from the ocean to the atmosphere, or the atmosphere to the ocean, depending on if it was getting warmer or colder. We all know that change the difference between being in an ice age and a non-ice age in the Earth is huge, and there would be
Right.
challenges for our civilizations to live in, at the cold extreme of this ice age.
Right. We wouldn't want to go back to an ice age.
Exactly. That was 80 parts per million.
Okay.
It took 80,000 years to move it backwards and forwards. In the last less than 300 years, we humans have moved not 80, but 140,
Oh my gosh.
140 per parts per million CO2 into the atmosphere. It has to make major changes. When we think what happened with a change of 80 parts per million, and now we've done 140 over a much shorter time period, it's changing all the balance you talked about in the very beginning. I was very impressed because you talked about interactions, and interactions is what it's all about. And when you push a button one place, something else happens somewhere else. And to sit here and think that changing the atmospheric CO2 concentration by 140 ppms isn't pushing a darn big button is so naive, it almost hurts.
Yeah, I we've been talking just about one um, of the nine boundaries, and I want to get to the others, but
Yes,
we
please.
are. Uh, but this is really important. We've talked about there. We can take action. We talked about acid rain and a treaty that removed or significantly reduced sulfur emissions, at least in Canada and the States, and it had good effects. We talked about a treaty that banned.
And in the United States, I mean, in Europe, we did it too.
Okay, good, good. I'm glad to hear that. I didn't have the knowledge, so I'm glad that. So we did this globally. No, that's great. We decided that CFCs, all the benefits that we got for that were outweighed by the harms. So we stopped making them. We banned it. We said you can't do it, and it got the desired effects. People stopped making it, and we allowed the ozone layer to heal, and that is what's happening now. We're identifying carbon emissions and other greenhouse gases as a major problem, and actually, in my view, even more significant than acid rain and holes in the ozone layer. And we seem to be failing miserably. Like the Paris Accord said that we need to keep us significantly below 1.5 degrees. We're at 1.5 degrees. We're
It said
going
it said
barreling.
it said keep it below 2 and aiming at 1.5.
Okay. All right.
Yeah,
So 1.5 was the goal. We're at that goal, and we're accelerating. If anything, there was a tiny drop, or a relatively small drop, noticeable, but a small drop in our carbon emissions during a global pandemic a few years ago. And then once the vaccines rolled out and the pandemic receded, and life got back to normal, we just ramped up our carbon emissions again,
sure.
and we're back at record levels once more. I promise this will be the last question on climate change, because I do want to get to everything else. But like, what is different about greenhouse gases and our inability to restrain ourselves from doing that, when we've shown that we, as a species, as a planet, have the ability to take harmful things that we're doing, recognize that they're harmful, and stop doing this harmful activity. We've done it before. We don't seem capable, or at least not based on current evidence, of doing so with carbon emissions. What's different here?
What's different is that what makes us unique as a species compared to all others is that we have managed to learn to harvest external energy and use it for our own purposes. It could be building a fire and getting heat and cooking. There is no other organism on this planet that can transport itself faster than it can run. We can. So it's this harvesting of external energy and using it for our purposes that makes us unique. And of course, that use of energy has permeated everything that we do, our transport, our production, everything. And so when you start talking about CO2, you're going directly into our energy and our energy use, and that's why it's so much harder than with CFCs. The interesting thing, and I think this is actually, to be honest, I think this is a good transition to move into the other boundaries, because
Yeah.
what the whole the planetary boundaries are based on a relatively young scientific discipline called Earth system science that understands how the Earth as a system works. It's a complex adaptive system, just like your family. I mean, it's, and if you don't just fix your family if it's dysfunctional. You have a vision for where you want to go, and you do lots of small things that bring you there. Now, the Earth system actually is controlled by interactions between the energy budget, which we could say is climate, and life. And it's the interaction between life and climate, then we can say, that causes the that creates these conditions that we're thriving in. And that means that the climate crisis and the biodiversity crisis must be just as important as each other. And to be honest, I'm more worried about the biodiversity crisis, or at least it scares me more than the climate crisis.
All right. So why? Talk to me about that. Because I have 4 kids, and I want them to thrive. And I'm not in any rush, but I would like ideally to be a grandfather one day. And if I do have grandkids, I would like them to thrive.
I can absolutely recommend it. It's great.
If my kids are listening, I'm patient. I'm not in a rush. I'm talking one day, but yes. So talk to me about biodiversity. Why? Like,
Why it
what?
scares me more?
Yeah, please.
Because when we get control over our emissions, and I say when, because we actually have all, or almost all, if not all, of the technologies that we need to do it today. We haven't made it so it can pay yet, and that's a big issue. We need to be focusing on how do we get our financial and economic system to support the behavior that we know we have to have. But when we get control over our emissions, it will take a long time. It will take thousands of years, but the energy balance of the Earth will go back to one that isn't affected by humans. It doesn't have a human fingerprint. But every time you lose a species, it's gone forever. So we can never go back to a biosphere, all living organisms, biodiversity, that doesn't carry the imprint of human activities. And that scares me. And you can say, well, evolution will make new, yes, but you'll probably have to wait 20 million years,
Right.
and it won't be the same biodiversity. So there still will be the fingerprint of human
Right.
activity.
The dinosaurs never came back after that meteor struck Earth, and I mean
Yes,
that's what allowed mammals and ultimately
I was going
humans
to
to
say
come by.
we can be happy about that.
Sure, but the reptilian ancestors are like, oh man.
Yeah, exactly, exactly. So that for me says that the biodiversity crisis and the climate crisis are equally important, and the news about them is equally devastating, to be perfectly honest. And in fact, in this Planetary Boundaries paper that you referred to, from it came out last year in September 23, we actually showed in that paper, we did some modeling work that said achieving the goals of the Paris Agreement are basically impossible if you don't actually manage to stop deforestation and preferably reforest as well,
Mhm.
because there's just so much carbon that that that's in the that's hiding in it. It's hiding in all the trees, and if you keep cutting them down, you're shooting yourself in the foot when you're trying to reduce the amount of CO2 that you're putting in the atmosphere. I should actually maybe also mention that this paper that came out last year has been downloaded now over 500,000 times. And for a scientific paper, that's very many times. The one we had in 2015 had only been downloaded 274,000, I think, after 8 years. And after 1 year, this one has been downloaded over 500,000 times. And that tells me this agenda, this understanding is is becoming more mainstream in society than you might think.
Well, I'll be sure to include a link to the paper itself. I mean, I'm not a scientist. I read it. It's legible to a non-scientist. It takes a little bit of effort, but I understood it. And so any of our listeners that are interested, just look in the show notes. There's a link to the paper there.
Leslie, I will give you another link to put that a paper we had that came out this week, which is much more accessible, which it's a review of the idea behind planetary boundaries and how much it's been used in society in different fields and so on. I
Wonderful.
will give
Yeah.
you
Well,
that too.
I'll definitely include that as well. Okay. So we've talked a fair amount now about two of the nine, or three of the nine. We talked about climate change, biodiversity, and ozone depletion. Uh, let's talk about what currently covers 70% of the Earth's surface, ocean, and
70% and growing.
yeah, unfortunately, yes. Unless we get the other things under control, it'll be significantly more than 70. So one of the boundaries is ocean acidification.
Mm.
Uh, Talk to me a little bit about that, please.
Oh, I will. But first, let me just note that we are unhappy about the fact that the ocean isn't more obvious in the planetary boundaries, because the ocean is really a great regulator of climate and everything else. Um, I think one of the reasons we've had trouble incorporating it is that the processes that happen there take a long time. For example, the 80,000 years it took to move 80 ppm CO2. Uh, so when we think planetary boundaries, we're all thinking lifetimes of people and political processes and so on. So it's been difficult getting the ocean really well documented in the planetary boundaries, and that's one of the things we're working on in the update. We're working on an update already, because you have to keep, as knowledge comes out, you have to keep updating this framework if it's going to be useful
Right.
for managing our relationship
That's
with the global environment. So we're trying to focus much more on getting ocean control variables in the.
you're living the ideal of the scientific enterprise. Thank
Yes.
you.
Okay. Sorry. Ocean acidification. Ocean acidification is, when you put more CO2 into the atmosphere and the ocean are always trying to get into equilibrium with respect to gases. They want to have just as much oxygen on one side as on the other side, and just as much CO2 on one side as on the other side. And so when you put more CO2 into the air, then more CO2 gets into the water. The thing is, when you put CO2 into water, you create carbonic acid. And that's why a lot of people go to the dentist and they're told that they have acid damage to their teeth. And it's because they're drinking too much carbonated beverage, that this is actually an acid, and it's dissolving the enamel in their teeth. And that's exactly what's happening to the ocean, that the ocean is becoming more acidic. And I mean, it's less acidic than your shampoo. So, I mean, you can easily continue to swim in the ocean. But the problem is that there are very, very many organisms in the ocean that have calcium carbonate or chalk in their shells. We're talking oysters, we're talking shellfish, we're talking lobsters and clams and corals and the tiny little organisms that sink to the bottom of the ocean and become the white cliffs of Dover and all that sort of stuff. So there's very many organisms in the ocean that create calcium carbonate. And when you have an acid and you put it in, or you put calcium carbonate in acid, and you do that if you put, for example, baking soda in vinegar, then the calcium carbonate dissolves. And this is what's happening for a lot of the organisms in the ocean that make calcium carbonate. On the west coast of the United States, where they do a lot of oyster aquaculture, it's already a problem when really, I would say, not say acidic water, but water with more acidity is pumped into the system, because you can imagine baby oysters have paper thin shells made of calcium carbonate, and they dissolve if it gets to be too acidic. So that's why we worry about ocean
So, so
acidification.
we, so we were talking earlier about how humans can only survive in a very narrow temperature range, and what you're saying is that there are a large number of animals that live in the sea that can only survive in a very narrow pH range, and even a
Exactly.
small increase in acidity uh, makes it impossible for them to live, or at least, to be slightly more optimistic, it's much more difficult. Much far
Challenging.
fewer will survive. Far fewer will survive in even a slightly more acidic ocean
Right. And of
than
course, there's
current
different, I
temperature.
mean, different kinds of organisms make different crystalline forms of calcium carbonate. And it's all very complicated, as you say. But the bottom line is, not a good idea to make the ocean acidic if you like organisms, or more acidic if
Right.
you like
And here we
organisms in it.
and again we get to the interactions, right? We Ocean acidification bad. That's driven by carbon emissions. More carbon in the atmosphere means more ocean acidification. Also,
Exactly.
ultimately, a warmer also increases, again, very slowly because there's so much water. But but ultimately the ocean temperature will rise, and so other organisms that are very sensitive to water temperatures are also going to be
Oh,
affected.
but Leslie, it's not going slowly in the ocean.
Oh,
The ocean it really, we don't know what's happening. And since 1979, we've been
okay,
able to measure the surface temperature of the ocean with infrared cameras that are on satellites. And so
okay.
we've been able to plot the whole year. And here you see the summer in the northern hemisphere, you see the summer in the southern hemisphere. Then you get the next year, and some months are a little warmer, some months are a little colder. It all
Right.
overlaps. Since 1979, it's been crawling up, but for every year, there's been overload. And that started in 2023 as well. It started, in fact, January 2023, I think, was the fifth warmest January ever in the ocean. I mean, that's no big deal in itself. And it kind of continued there. And then in May 2023, bloop, the average temperature of the oceans rose with, on average, zero point 0.2 degrees centigrade, which is a huge jump. And
Oh my gosh,
you've
that's
got all
that's
this,
enormous.
it is. And this is continued. The temperature of the ocean is way above all those other lines. They look like spaghetti on the graph there. But now suddenly, boink, we've gone up, and we're still there. And the really scary thing is, we don't really know why. Some people say, oh, well, it was an El Nino year. Yes, but I promise you, we've had El Nino
Well,
years.
that's every 7 years, right?
Well, sort of, more or less. But
Okay.
yeah, since 1979, there have certainly been El Nino years. And some people say, well, climate change, yes, but since 1979, we certainly have had climate change. And then people say, well, it's because the ships have stopped using um, fuels that give off sulfur particles and cool the. You do the numbers, it doesn't work. And then some people say, well, there's been underwater volcanoes and they've put more water vapor in the air, and you do the numbers and it doesn't work. The bottom line, we don't know why. And I think that's really scary. I think it should humble us tremendously because, the people who do the climate models say, well, the models are only accurate to within, 66%, so we're still within the margin of error. Yeah, that's fine. That's fine. I'm not criticizing the model. It's just that the model doesn't explain what happened. And that doesn't mean the model isn't good. It doesn't mean that it isn't robust. A model is only a mathematical recipe describing our understanding of the climate system. And when the model doesn't do the same thing as the real world, or the real world doesn't do the same thing as the model, it says, we don't really understand this very well. And something may have changed. We just don't know what it is. And when over 90% of the extra heat being stored near this planet, which is causing climate change, is in the ocean, and the ocean takes such a jump, it means the whole climate change has just taken a huge jump. And remember
Hmm.
how many records were broken in the air because the ocean gives its heat off to the air in 2023. And even though we're not finished with 2024 yet, we already know it's going to be the warmest year ever, and the first year in which the average temperature for the year is over 1.5 degrees above the pre-industrial. So the ocean, don't say it's going slowly. It's going
Okay. No, no,
very
no.
quickly.
And that's why I like talking to people like you. Like I said, my knowledge is incomplete, and so now I won't say that. I won't say that it's going slowly anymore. It's. I was about to say it's good to know, but actually, it's not good to. I mean, it is good to know, but what you're saying is scary. I'm reminded of a movie I saw a couple years ago, a Netflix movie called "Don't Look Up," and the basic premise is there's a giant meteor hurtling towards Earth, and it's like big, like the meteor that wiped out the dinosaurs type. Like it's an extinction level event,
A bad news
and
event, yes.
one of the politicians, I mean, it's an American movie, so of course everything happens in the United States. There's a politician running for president whose campaign slogan is, "It's going to be fine, don't look up." It's so big you can actually see the trail in the sky as it's hurtling towards Earth. It's going to kill everybody, and the politician's campaign slogan is, "Don't look up." And it is a brutal satire. It's a good film, but it was also hard to watch because the mentality of the people of the fictional characters in the film, they're short-sighted, they're venal, they're stupid, and I recognize them in the
Correction,
real
no
world.
comment.
Uh, and so a lot of this conversation, like there's a reason this is coming to mind. Like what you're what we're talking about, things that will um, destroy our way of life, our civilization, our ability to harness energy, to flip a switch and turn on light, to have a global communication system so that I'm sitting here in Toronto, you're sitting there in Denmark, and we're having a real conversation. And then this is going out to everybody that wants to listen to it everywhere in the world. Not only is that threatened, but actual human life might not survive. Huge disruptions, and we don't seem to be taking it very seriously, or because as your title says, like you know we need all 9 planetary boundaries to be safe. If any one of them gets too far out of whack, then again, human life is threatened. 6 of them are out of whack, and of those 6 of them are getting worse at an accelerating pace. I think that this is something that needs a lot more attention. It's one of the reasons why I wanted to speak with you and why I'm happy that we are having this conversation. But uh, I really think we need to get more people thinking and talking about this, and in the hopes that if more people think and talk about this, it will lead to more action. I like I said, I'm thinking not just of myself and what you're telling me about the oceans, I don't need to think about my possible future grandkids. Uh,
You're going to be in real trouble on the home front.
yeah, like just I'm hoping to have a few more decades of my life to enjoy. There's a lot of things I want to see and do and accomplish, and just my own life is way of life is in danger, it would seem.
Yes, I mean, this is existential, but I am an optimist. I do
Great.
actually believe that I think, everybody realizes Darwin really shook society in 1859 when he came along and said, "Hey, we're a product of evolution, just like all other organisms. We're nothing special," and that it really shook society, and it actually shook the economic paradigm of the day as well, because a lot of countries didn't think that you could have economic growth or wealth if you didn't have slaves. And when the scientist comes along and says, "Hey, those aren't animals," it kind of shakes the whole business. It took a very, very long time for people to accept that we are an organism. And in fact, in some states in the United States, you can't even teach about evolutionary theory. So this is almost 200 years later that we're still struggling with this. And I think at the moment we're going through a similar sort of transition in our understanding of our relationship to the world around us. And I think that period started when we started getting those satellite pictures. No, they aren't even satellite pictures. Those are the pictures that were taken from the Apollo mission of the Earth from space.
Right.
And
Earthrise.
exactly, exactly. And what's happening in this phase is that we're beginning to realize that not only are we an organism just like all others, but we are a part of an ecosystem just like all others. And if we don't
Hmm.
respect that ecosystem, then there isn't a future. Now, obviously, not everybody's there, but I said earlier that the 2015 Planetary Boundaries paper was downloaded 274,000 times after 8 years. This one, over a half a million in 1 year. It shows that this is accelerating this understanding. And 20 years ago, nobody would have thought that your gut flora were interesting for anything except your digestion, and now we know they're important for your mental health and your immune system and so on. We're beginning to realize that it's interactions that are important.
Yeah, and actually on exactly that topic, if any listeners are interested more about gut flora, I spoke with Emma Allen Verco. You can look
Oh,
back about
wow.
2 years ago, and you can learn a lot more about gut flora by listening to the podcast for Inquiry episode with her. That one I learned so much from her. So
but
check out our archives if gut flora interests you.
But it's all about interactions, whether they're in
Interactions,
our
right?
body or whether it's in the planet as a whole. And this is a real challenge for our societies and the way they work, because our school systems don't study interactions. When we go to university, we get into, this is my box, it's geology. This is my box, it's economics. This is my box, it's humanities. And it's as if we think if you could get all the details in those boxes right and put all the details into a pot and stir up the pot, you'd understand how the whole world works. Well, that would be like asking all the doctors with their different specialities to put their knowledge about brains and hearts and stomachs and feet and reproductive systems in a pot, and then you'd understand what a person is. But it's the interactions between those parts that are
Right.
important.
The respiratory system interacts with the circulatory system, which interacts with the digestive system, which interacts with the renal system, and they all interact with each other, right? It's not just one. It's not a linear thing with this interacts with this one, with this one, this one. It's like they're all in a circle, and there's lines between all of them,
But
and
we don't.
everything affects everything else.
But thanks to the good Newton, who made us all into reductionists, we don't study interactions. We study things, living
Right.
and non-living things.
Well, then I think it's time we have to. I mean, we do need to understand how things work in and of themselves, but that's only the start, right? And then we go to the next level. Like that's a foundation level, but genuine understanding comes from knowing not just how it works in itself, but how it interacts with all the other systems to for its inputs and its outputs, and how it's changed by what other systems do, and how it changes those other systems, which in turn changes its reaction to yourself, or the acting body.
And this points to another problem that the planetary boundaries really illustrates for us, and that is
Mm-hmm.
in our international agreements, we put climate in one corner with the UNFCCC, we put
Yeah,
biodiversity in another corner with that convention, and then we have over in the other corner we have pollution, and you can't do it that way. I mean, we're missing all of the interactions. And as I say, it looks like from our study, it looks like give up solving the climate problem unless you're also going to solve the biodiversity and the forest problem at the same time, because you can't do it in your
in
own little
isolation.
box. You have, yeah,
Yeah.
exactly. And I don't see, well, actually, I do see. If you think about the Sustainable Development Goals that were adopted in the UN in 2015, and people didn't really catch on I don't think they caught on in North America. They caught on pretty well in Europe, but now they're fading because our attention span is very short. But what was interesting about that was the fact that 17 goals were identified within 17 different boxes. But in all of those boxes, we knew we had challenges far before 2015. And in fact, we had UN agreements on climate, on biodiversity, on women, on health, on water, on peace. I mean, all these things that are in the Sustainable Development Goals. So what was new and different with the Sustainable Development Goals and Agenda 2030 was that all these challenges were brought into the same framework. And when you do that, it's not the boxes themselves that are interesting, it's the interactions between them that are interesting. And I think actually at the if we're going to keep on this idea of interactions,
Mm-hmm.
most people think that primitive societies or less developed societies, I'm sure it's politically incorrect to talk about primitive, but less developed societies lived in harmony with nature. No, they didn't. They took everything they needed, be it game or trees to burn to get energy or whatever from nature, and they let their waste, their bodily waste, for example, fall wherever it was produced. And then they realized, no, no, we're getting sick from polluted water, polluted with our own bodily waste. We're running out of game. We need to make some rules here. You can only come out to get rid of your waste over there. You have to take only the game you can use. You have to use the whole animal. You can't take the pregnant one, and you have to share it with the whole team. And the whole. So they managed their interactions with they were aware of them, and they managed their interactions with the world around them. When we created a global economy, we divorced ourselves from our interactions with the world around us. We don't see the poor child on the other side of the world who makes the cheap clothes we buy. We don't see the biodiversity that gets lost in South America or Southeast Asia to make palm oil for our food or soybeans for our pigs. And I think what we're really talking about at the moment is getting back into contact with these interactions. Right now, we're operating with economic models where we call these interactions externalities. And if you accept the fact that we're a part of a system, an ecosystem, and we need to respect that ecosystem, then nothing is external. We're going to have
Right.
to actually incorporate these externalities. And at the moment, you can use, because it's climate and biodiversity, that it's their interaction that creates the conditions on Earth, we can use them as proxies for the Earth's resources. And we can see that they're both that our goals are we have goals for where we want the climate to be and where we want biodiversity to be. And we can see we're getting farther away from those goals for every day that goes. but we're going better on many other goals. The goals that have to do with people. We're getting, child mortality is, or infant mortality is going way down. Neonatal health is there are lots of things about people that are getting better, while at the same time the climate and biodiversity are going down. And you say, well, I'm a people person, so I'll do the people stuff first. And if we have the time and the inclination and the money, then we'll do the climate and biodiversity stuff later. You just can't do that because it's actually the climate and the biodiversity, the Earth's resources are a real currency. We don't get rich from using money. Money's just a proxy for the Earth's resources, and it always has been. Our ancestors bought and sold from each other using naturalia, and then they realized that, oh, wait a minute, Leslie might not need bread right now. Here, you can have this shell, and you can exchange this shell for bread when you need bread. And then money was born. And for a very long time, we had a gold standard behind our currencies, just to keep reminding us that they actually had something to do with the real world, because every organism survives by using the things in the real world. And then, of course, we took away the gold standard. But we can't take away the fact that we can't eat money. We can't live in money. We can't put money on to stay warm.
Right.
It's still going to be the Earth's resources. And the planetary boundaries try and bring us back into contact with those Earth resources before we use them all. Because
Right.
you can party even though your bank account, the balance on your bank account's going down. You just can't party forever. And now we're back to those grandchildren that you hope you're going to get one day. If we
Hmm.
want them to be able to party as well, we're just going to have to break the curve and bring the climate and biodiversity trends, instead of being negative, hold them steady.
All right. I do want to get to the other. There's so much I want to talk about, and I'm at risk of asking to keep you on for hours and hours and hours. But I want to respect your time and our listeners. Let's talk about biogeochemical flows. There's phosphorus and nitrogen, uh, essential essential in our biology and that of all plants and animals. That's one of our planetary boundaries. Uh, it was new to me actually. So talk to me about nitrogen and phosphorus.
Sure, but let me emphasize it doesn't. We use nitrogen and phosphorus as the examples today because those are the geochemical cycles on Earth that humans are impacting most. The biogeochemical cycles that humans are impacting most. If you look at what the nitrogen cycle looks like without people, and then look at what it's like now, it's entirely different. It's much more corrupted by human activities than the carbon cycle. But we do actually write in some of the stuff that we do that it doesn't necessarily have to be confined to just nitrogen and phosphorus. It might be things like oxygen or silicate. I mean, there's lots of or silicon. There's lots of potential candidates to come into this category. But the idea is life's role in this planet is to move around the elements. And there are these geochemical cycles and or biogeochemical cycles, and then humans come in and they corrupt them. And you can say we used to think that that smoke coming out of a smokestack was a local environmental problem. Now we realize it's a global problem, and it's the same with nitrogen and phosphorus. That we think, oh, it's a local pollution problem, but no, you actually start, because you're mobilizing so much reactive nitrogen, you're creating much more nitrous oxide, which then feeds back into the climate cycle and so on. So the argument here is that when these element cycles are so important for maintaining the Earth in the state that it's had for the last 10 to 12,000 years, then there must also be a limit as to how much humanity can allow itself to alter those cycles. That doesn't mean it's a bad thing to use nitrogen or phosphorus. What it means is that we should not be leaving behind waste all that extra reactive nitrogen and phosphorus. And if you look at the
Again,
planetary,
Goldilocks, right? You can't have if we can't have too little, can't have too much. There's a range that is just right, but we have to stay within that range. Is that
yeah, absolutely. But there's also, and it's in planetary boundaries are trying to figure out what the range is.
right?
But one thing I haven't mentioned about the planetary boundaries, which I think is really interesting, is that we three of them, and that is biodiversity, the land use change, and use of water, have to do with us taking something out to survive.
Hmm.
The other six are all about waste, our waste products.
Okay.
And if you think about nature, nature has been surviving on this planet for 3.5 billion years. And it's a planet with limited resources. How has life managed for that, wow, between 3 and 3.5 billion years? How's it managed without running out of resources? It doesn't create waste. It has 100% circular economy. And six of the nine planetary boundaries are about waste,
Right. So my
including
waste products is somebody else's food, which becomes and their and
that's what
its
nature
waste
does.
products is the food for something else, and that cycle is powered ultimately by the sun. The energy to
Exactly.
move things from one organism to another to another to another is powered by the sun. But ultimately there is waste, but then that waste is someone else's food,
Exactly.
and
So
so there's no
you
there's no
reduce
there's no there's no loss to the system. There's no waste that isn't picked up by something else, and that's what makes it sustainable.
right. And think what we're trying to do now. Oh, we're going to catch the CO2 and then we're going to bury it. Okay, there was our waste, and now we're going to throw it away instead of having it in the system. I'm a little
Right.
worried. I'm a little worried by that strategy. But you said something very interesting here, which reminded me that we haven't discussed the 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 photosynthesis. You say it's all powered by photosynthesis, and one of the really interesting things I think we did in the last planetary boundary paper was we said, okay, we have a metric for biodiversity loss, which is rates of extinction,
Hmm.
and how many are we losing? How many species are we losing? That's really important because different species is what gives life its resilience. I mean, life has survived under all these different conditions that the Earth has had in the 3 or 3.5 billion years that life has been here, and some species that don't look important today may be very important in other under other climate conditions or other Earth conditions. So that's an important one. But we don't we haven't found it if it's there that there's a relationship between numbers of species and this function that life has where it moves around elements and stuff. So numbers of species may not be the driving factor there. So we said, well, we need a metric that tells us something about what's moving around. And so we said, well, photosynthesis. We all learned in somewhere like third grade that photosynthesis is what feeds all living organisms on this planet. And so we said, well, let's go in and try and see how much photosynthesis was there on this planet in the 10,000 years before the Industrial Revolution. How much was there every year? Turns
Right.
out it was incredibly stable, but that's because the conditions were stable, the temperature, the light, all that sort of stuff. It also turns out that we humans are taking a third of that. That is to say, we are taking a third of the energy that all of life was supposed to have, uh, and using it for our own purposes. And that, of course, is energy that the rest of life isn't getting. Now, that has to be a driver of the loss of biodiversity. And some people will rightly say, but there's more photosynthesis today because we've put more CO2 in the atmosphere and there's a fertilization effect. Yes, but that extra photosynthesis is buffering climate change. So if we harvest and use that, then we're back to the climate change problem. So let's just say let's look at how much photosynthesis there was in the 10,000 years before the Industrial Revolution and say, okay, we're taking a third of that for our own purposes. And now we're talking about, now we're going to have a bioeconomy. We've always had a bioeconomy. Coal, oil, and gas are also products of photosynthesis. But we've now
Right.
realized, yeah, we've now realized, hey, it's problematic to use photosynthetic products that were made 200 million years ago. We're only going to use photosynthetic products being made today. Well, there's a limit. There's a limit to the amount of photosynthesis that's taking place. It's not unlimited, and we do not increase it with our agriculture. Think of a barley field. It's only, I mean, it's green from April or March, April to July, and then it's brown and it's not doing photosynthesis. And we're doing everything within our power, chemically and mechanically, to make sure other plants don't come in and do photosynthesis in that field. So we build infrastructure, which means there's no photosynthesis there where it used to be. We reduce the amount of photosynthesis, and and we're already taking a third of what is available to run life, and we want to take more, more, more. And this, I think, is something we need to focus much more on. We're not as smart as plants. We can't do photosynthesis. If we could do fusion, we'd be in a good place. But I'm so old that I can remember 50 years ago, people said in 20 years we'll have fusion. And now they're saying in 20 years we'll have fusion. So we can't.
I spoke with Alan Offenberger about a year and a half ago on the current state of fusion technology. So you can learn about that too in a previous episode.
Oh, well, I will go in and have a look at that because
Yeah.
given my age, it's interesting to try and understand why it didn't happen when everybody said it was gonna come. So anyway, the point I was trying to make is that we're not smart enough to do photosynthesis
Mm-hmm.
ourselves. But I think we are smart enough to help plants do photosynthesis places where it hasn't done it before. Places like the bioreactors, small organisms in bioreactors, or even using the surface of the ocean. There's lots of light that comes in there. We can have, all sorts of farming activities or whatever there, and we could use some of this material to make both human but also animal food. I mean, I think we really, really have to try and both increase the amount of photosynthesis that there is by helping plants do it somewhere else. And also, we need to use what's produced much, much more efficiently. We refine oil and get all sorts of different chemicals out of it that we can use. And there are lots of chemicals in the plants that grow today. But what do we do with biomass? Yeah, we burn it to make heat. Well, that's nice, but we're burning a lot of good chemicals that could be used in industry and other ways as well. So I think we haven't accepted the fact that this, ultimately it's the products of photosynthesis that keep us all alive. They're limited. That is the key to the future. And we have to use that stuff as efficiently as possible.
All right. Talk to me about freshwater change.
Freshwater change is one of the ones that we've changed radically over time. When we first started doing this, we looked only at the water that we were taking out of what we call blue water, taking out of rivers or lakes or whatever, and changing the flow of water. This time with the new paper, we've actually included green water. What is green water? Green water is water that's in the soils, for example, and it can be used by plants. And in many ways, green water may be more important for biodiversity and actually also for the climate than blue water. So and one of a good example of a change in green water is permafrost. That when we start melting the permafrost, then the the water that's there that was ice can become water vapor and so on, which changes the chemistry totally, the way we do irrigation, all that sort of stuff. Irrigation, draining, it all changed. Draining peat bogs. Suddenly we've got a lot of carbon coming out of draining peat bogs. So changing where and when water is available in the system has knock-on effects all over the place. So the metric that we've decided to use for both the blue and the green water is the degree of change that's come about since the Industrial Revolution. And obviously we give we don't say it has to be just like it was before, but there's some enormous changes we have made on this planet with where and when water is available, and it's changing climate, it's changing biodiversity, and those are the two things that we have to keep an eye on.
Excellent. We've got two more, and I do want to cover both quickly if we can. Atmospheric aerosol loading.
That's dead easy. That's dead easy.
Okay.
Um, you talked about the dinosaurs. Meteor. What happened?
Yep.
Lots of particles in the atmosphere. The sun didn't come down, and so on. We know particles in the atmosphere can change the amount of heat reaching the Earth, and we know that they can change the distribution of rain, for example, on because they make cloud condensation nuclei. So air pollution is particles in the atmosphere. I'm quite optimistic about that boundary because we know air pollution isn't good for us, so we're trying to stop it anyway. But it has a global effect. And what we use as the metric there for looking at particles in the atmosphere is the ratio between how many particle I mean how murky is the air because of particles in the northern hemisphere compared to the southern hemisphere, because we know that ratio can be important for the distribution of the monsoons around India and so on. I don't think we're going to cross that boundary because we're interested in air pollution for other reasons, but it is a global player that if we changed it enough, think of the dinosaurs, um,
Hmm.
then we would change conditions of living conditions on Earth.
Actually, no, and I think that's great. I mean, I talked about the meteor impact killing the dinosaurs, but that was not act. It wasn't the impact itself. I mean, it killed many
I
that
was saying
were
there may
in
be
the
some
area.
that got it on the head, but most of them it
Yeah,
was
but the reason they went extinct was not the impact directly, but the aerosol loading as a
yes,
result
exactly,
of the impact. All right,
exactly.
and the last one is novel entities, and
Yeah,
I want to read a couple paragraphs from your paper because this jumped out at me when I read the paper. I had to actually put it down and take a walk before I could resume. So let me just read a couple paragraphs from your paper. Hundreds of thousands of synthetic chemicals are now produced and released to the environment. For many substances, the potentially large and persistent effects on Earth system processes of their introduction, particularly on functional biosphere integrity, are not well known and their use is not well regulated. The only truly safe operating space that can ensure Holocene like conditions is one where these entities are absent unless their potential impacts with respect to the Earth have been thoroughly evaluated. This would imply that the quantified planetary boundary should be set at zero release. And then this is the kicker: approximately 80% of these chemicals have been in use for at least 10 years without yet having undergone a safety assessment. Yikes.
yeah, yeah. The thing is, you have to think, Leslie, about the fact that evolution has been going now for something, as I say, something like 3.5 billion years and has created a fine tuned machine. And we humans have this wrong idea that we humans have this fallacy in our minds that we are better than nature and we can find something that's going to fix a problem that we think we have. Something like DDT, something like CFCs, something like we have so many good examples of putting things into this environment, into the open environment that haven't been a part of this evolutionary process and just really mess it totally up by interactions we hadn't seen. Rachel Carson wrote about this brilliantly in the 50s and 60s.
Silent
And
Spring.
Silent Spring, yes, and the sea around us and so on. But Silent Spring, yes, and it is yeah, it's amazing to me that we haven't yet learned the lesson that we're not smarter than nature. And by just putting some chemical out there, we're going to be surprised. We're still getting surprised by our flame retardants that turn out to be persistent chemicals that are coming into the ocean, or but it's obviously there are dangers associated with just putting things that don't belong there out into the system. Plastic. I mean, we have been throwing out plastic since the 1950s, knowing full well that it's basically non-degradable in nature. That's why
Yeah, we
we
have
like it. That's why we like it. And
a
now we're finding plastic particles in the brains of dead people, in our lungs, in men's penises. I mean, people say, well, we don't really know that it's dangerous for us. Come on. I mean,
it
it,
can't be good.
yeah, let's look at it that way. And my one of my sons says, I'm guessing this microplastic pollution is my generation's asbestos. That, was asbestos for your generation, it's microplastics for mine. No, everybody thought plastic was a wonderful thing. I mean,
Yeah.
I have a picture from Life magazine from the 1950s of a family, mother, father, two children, jumping for joy and throwing plastic over their shoulders. Plastic forks and knives, and this is wonderful. And yet it came back to haunt us, and
Right.
we just have to be much,
Well,
much more
there's like this
careful.
mismatch of timelines, right? We have a 10,000 year product that we're using once that is useful to us for like a week or a month or something. And so then that that's essentially zero in terms of a 10,000 year lifetime. We should probably engineer something that lasts roughly as long as it's useful to us. And uh,
You said something earlier in this podcast where you said we need to be checking that the benefit we get from something it outweighs the costs. And
mhm,
I think we've been focusing too much on the benefits. And in fact, I mean, sustainable development. I mean, nobody's going to say anything negative about sustainable development, but most people will say, "Oh, but I'm glad somebody else is worrying about it. I have something more important to do."
right,
I mean, what is sustainable development? You said earlier you want this world to be a better place for your children, not necessarily in material terms, but I want my children to have better health, to have more time with their family. I mean, to have a better life. Development's a no-brainer. And we know that there are many people on this planet that also need material development. Sustainable. That just means that it can carry on as long as the eye can see. And as long as we can see the biodiversity and the climate crisis, and that we don't manage our relationship with the global environment, we know this party can't continue forever. And
right.
what is sustainable development? It's making sure that when you use the Earth's resources, and we will do that, all organisms do, that we do it with a minimum of environmental and social costs. And that's the ratio that we need to keep in mind at all times. I'm
Yeah, I'm thinking about this like in economic terms. Like if you like, over 3.5 billion years, the Earth has like savings, right? It's got a bank account and it's full. But as long as we keep doing things in an unsustainable manner, that balance is going to decrease. And you know what? If I make a certain amount of money and I spend more money than I make, as you were saying, the party goes on and it's great as long as it lasts. I think it was Hemingway who famously wrote, "How did you go bankrupt?" And then the answer was slowly, then all at once. And I feel like we at some point we're going to declare environmental bankruptcy. And you know, in human terms and in economic terms, we have a process for bankruptcy where your debts are forgiven, or and you get punished, and for several years you have to hang your head in shame in the penalty box. You can't do certain things, but then you move on. If we declare environmental bankruptcy, well, we won't declare it, but if the environment declares bankruptcy, that's going to be a catastrophe. That's where we get to these apocalyptic scenarios for human civilization. So we need to get to the point where we're spending in environmental terms, no more than nature can regenerate. And we can help nature regenerate a bit faster, which means we can spend a little bit more. But I don't want to hit the catastrophe point. And it seems that we're on that path at the moment.
You're totally right. I mean, the environmental component of sustainability is that our demand, back to economics, our demand for the Earth's resources is within their supply. And right now, in your country and in my country, if everybody lived with the same demand, everybody on this Earth lived with the
Mhm.
same demand that we have, we would need more than 4 planets. So getting the demand for the resources to within the supply is the environmental part. The social part is how we share those limited resources among
Mhm.
what soon will be 10 billion people plus other life on Earth. And at the moment, there are less than 1% of the Earth's population that owns more than the 50% who are poorest. So at the end of the day, sustainable development is also an ethical question.
I completely agree, Catherine. You've been very generous with your time and with your thoughts. Are there any last ideas you'd like to share with our audience today?
Yeah, I'd like to say I think this is an incredibly exciting time that we're living in. It's challenging, it's frightening, but if we assume that everything is going to uh, be smooth sailing, we are in a transition. It's wrong to assume everything's going to be clear sailing. There'll be bumps along the way, but I honestly believe we've gotten to the point now that so many people want this, it's going to happen. The only question is whether it's going to happen in time.
Well, that's why we need people like you, and hopefully the people that listen to this podcast can take action. And for our listeners in Canada, if you're motivated by what you hear, please email me podcast at Center for Inquiry. If you're a writer, if you're a scientist, and you want to contribute, uh, you know. We welcome volunteers. We welcome science writers. We welcome scientists to join us. I think this is one of the most important issues facing well, our species, really. So, Katherine Richardson, thank you again for taking the time and speaking with me today on Podcast for Inquiry.
A great pleasure, Leslie.
If you enjoyed today's episode, please show your support at patreon.com/podcast for inquiry and give us a 5-star review. Email us at podcast@centerforinquiry.ca. We'd love to hear your perspective. The Podcast for Inquiry is brought to you by the Centre for Inquiry Canada, a national educational charity supporting reason, compassion, and secular values. Help us support rational discourse and evidence-based decision-making by becoming a member at centerforinquiry.ca/join. CFIC is on the web, centerforinquiry.ca. We are on Facebook, and follow us on Twitter or X at CFI Canada. Podcast for Inquiry is produced and edited by Zach Dumont and Martin Zielinski. Music by Anthony Lazaro. I'm your host, Leslie Rosenblood. See you next time.